Okay, so welcome everybody. So today we have Steve Oudot from INRIA, who will be talking to us about signed barcodes for multi-parameter persistence via rank decompositions. Thank you.
All right, thank you, Hanan, and thanks to the organizers for the invitation. So this is joint work with Magnus Botnan and Stefan Opperman. And down here, you can see the link to the corresponding draft on the archive. So our goal here is to find or define a compact and interpretable summary for the rank invariant. And as you will see, all the bullets here are all you can see in the paper. So that's quite a lot of stuff. So I will probably not be able to cover all of it. I'll try to cover it in this order, and I'll stop whenever I run out of time. Okay. So this will be about the rank invariant, about representing it. We're going to work with representations of posets. Posets will be can be very general in this work, and so these will be representations of general posets over a fixed field K, and so these will be functors from the poset seen as a category to the category of vector spaces over K. Generally, the vector spaces will be finite dimensional, but sometimes they will not be. So that's why I'm using a capital V here. And among these representations, the ones that are intervals are going to play a special role. So an interval representation is a thin representation. It's the indicator representation of an interval. So its support is an interval, where an interval in a poset is simply a convex connected subset. These are indecomposable representations with local endomorphism ring. And among these intervals, some of them will play a very special role. So the first type of interval that will play a very special role are the segments, where the segment defined by two comparable elements of the poset S and T is the collection of elements in the poset that lie in between these two elements for the order in the poset. And so, for instance, if the poset is R2 equipped with the product order, as on the right-hand side, then this closed segment is simply the closed rectangle joining S and T. And the other family of intervals that will play an important role are what we call the upper and lower hooks, which are defined respectively here and there. So, as you can see on the right-hand side, basically an upper hook is the set difference between the upset of a given point and the and S and the upset of a larger element T. And dually, lower hook is the set difference between the downset of an element T and the downset of a lower element S. Most of the time, I will be talking about segments, though. Let me go over the one parameter case, which I'm sure everyone here is familiar with. Just to set up a baseline of what the different properties that we're targeting here for our say visual representation of the rank invariant. So in the one parameter case, the poset is the real line or a subset of the real line. So in this example here, the poset is just the natural numbers 1 through 5, and representation is simply a diagram, and it's indexed over this totally ordered set. So here's an example of a representation, and a description of this representation is given by its rank invariant, which is defined as the collection of ranks of the internal morphisms of the representation for every comparable indices S and T. So in the one parameter setting, there's a nice way to represent the rank invariant as a function over the plane, a real function or integer valued function over the plane, as you see on the right hand side. And actually the function is defined over the half plane above the diagonal, because S is always less than or equal to T. And as you can see, the graph of this function is in fact the graph of the counting function of an arrangement of triangles whose bases lie on the diagonal. And so the rank invariant is fully described by the collection of the apices of these triangles, as you can see in blue here. Each apex corresponds to a given triangle, which has a certain base, which is an interval. And so the collection of these apices is called the persistence diagram associated with this rank invariant. And the collection of bases is a barcode, which is called the persistence barcode associated with this rank invariant. And this, algebraically speaking, this corresponds to decomposing the rank invariant as a function over so this upper half plane as a function of, decompose it as a linear combination with positive coefficients of rank invariants of interval modules, where the intervals here are exactly the intervals in the barcode. Equivalently, this is the same as expressing the rank invariant of M as the rank invariant of some interval decomposable module. Okay. And so this gives a way to interpret and visualize compactly the rank invariant. In particular, you can say that whenever the rank invariant increases, whenever the rank invariant increases, like here, when you go from here to there, that means that there is some feature that appears. Okay, and the lifespan of that feature is represented by one interval. And dually, if the rank invariant decreases, then that means that there is the end of the death of a certain feature. So the end of its corresponding lifespan. And so in particular, if you want to know what is the rank between two indices, for instance, 2 and 4 here, all you need to do is to count the number of intervals that span the range between 2 and 4, or equivalently, the intervals that connect the downset of 2 to the upset of 4. So in this example, this number of interval is 1. So this is nice because it not only do you get a compact representation of the rank invariant, and you can interpret it. Another thing that you can do with this interpretation is to understand what is the signal and what is the noise. So like long intervals will naturally correspond to long-lasting features, and you can interpret them as being the signal in your rank invariant and therefore in the corresponding module. Whereas the short intervals you can interpret as being the noise, And this is the usual interpretation that people are using in applications in TDA. So in the one parameter setting, what is nice is that this functional decomposition or decomposition at the functional level corresponds to an actual algebraic decomposition of the module itself. So basically the intervals that you see in the barcode here are the same as the ones that play a role in the direct sum decomposition of the module. So this is why the persistence barcode or diagram is actually an invariant and a complete invariant, not only of the rank invariant itself, but of the module that the rank invariant originates from. Finally, you can compute it pretty easily, at least point-wise. For instance, if you want to know what is the multiplicity of this point, there is an inclusion-exclusion formula that gives you the multiplicity in terms of the values taken by the rank invariant over a certain grid. So this is all very nice, and this is what we would like to get in multi-parameter setting. So let's try to do the same thing. Let's take P to be now, for instance, a grid in R2. Okay, so this 3x3 grid here. And let's take a representation of that grid, such as this one, and let's ask ourselves, can we express the rank invariant of that representation as the rank invariant of some interval decomposable module? So I chose this example on purpose because for this example, it is not possible to do that. And let me explain why. So if you see these identity maps here and there, because of these identity maps, if you decompose your rank invariant as a sum of rank invariants of interval modules, you will have one of the intervals that contains this whole square. Likewise, because of these two identity maps here, you need to have at least one of your intervals that contains this whole square here. Now the question is, do these two squares belong to the same interval in the decomposition, or do they not? If they do, then that means that you have an interval that contains this shape. And unfortunately, because of this, the rank that you have here must be 1 at least. Whereas in the original module, this rank is 0. If you compose these two maps, you get 0. So these two squares cannot belong to the same interval. So they have to belong to different intervals. But then if they do, what's happening is that the rank that you get from this index to that index is going to be 0. And there's no way for you to add more intervals because, as you can see, point-wise, the dimensions of your representation have been filled in by your two squares. So this example shows that what we are doing in the one parameter setting cannot be done, at least as it is, as I presented it, in the higher parameters and with higher numbers of parameters. Fortunately for us, you can do it by taking not only positive terms, but also negative terms in your linear combination. So here's an example of a linear combination of rank invariants of interval modules that gives you that equals the rank invariant of the module on the left-hand side. Okay. And here's another one. And there may be many of them, actually. This may not be unique. What's interesting about this one in particular is that the intervals have a very particular and simple shape. They are rectangles, so segments in general. And so the question that this example raises is twofold. First, when do such decompositions exist? Namely, under which conditions can you decompose the rank invariant of a representation of a poset into a z-linear combination of rank invariants of segment representations? And under which conditions can you have uniqueness of this decomposition? So these are the two questions I'm going to answer in the next few minutes. So before answering these two questions, I need to define formally what I mean by a rank decomposition or a signed rank decomposition in this case. So again, we're going to work with an arbitrary poset and we're going to take representations over a fixed field K. And now I'm going to be interested in the collection of segments in that poset. Okay, so again, segments in the multi-parameter setting are going to look like rectangles. And now I'm going to consider the rank invariant of M as a map from the collection of segments to the integers. Why can I do that? Just because the rank invariant is a map over the collection of comparable indices in the poset. And this is exactly the same as the collection of segments because a segment has two endpoints. So I'm going to take it this way. And so more generally, I'm going to consider rank decompositions of functions from that collection of segments to the integers. Okay, not only rank invariants, but general functions. I'm going to ask the previous two questions here more generally than for just rank invariants. Okay, I'm going to take arbitrary functions from the segments over P to the integers. And so signed rank decomposition for such a function will be defined as a pair R comma S, so curly R comma curly S, of multisets of closed segments in the poset. I'm asking these multisets to be pointwise finite, namely at every index in the poset, there is only a finite number of elements of R and S. Okay, this is to ensure that the ranks are going to be finite, such that the function R is expressed as the difference between the segment decomposable representations defined by R on the one hand side and defined by S on the left, on the other, sorry, on the one hand, and by S on the other hand. So here a bit of notation. So K sub curly R will be this direct sum here, and K sub curly S will be that direct sum over there. Okay, just to simplify things. And if you think about it just a few seconds, you realize that this cannot give you uniqueness. I mean, when you define rank decompositions this way, it's obvious that actually they cannot be unique. Why? Just because you can always add one more term here and the same term over there. Okay, so if you add the same rectangle to R and S, you're going to get the same difference, but still, but of course, you'll get a different pair R and S. So this brings up another concept, which is that of a minimal rank decomposition, which adds the axiom that R and S have to be disjoint. Okay, so we're going to say that a rank decomposition is minimal when the two sets curly R and curly S are disjoint. And now it's easy to see that such minimal decompositions exist as soon as decompositions exist in the first place. So if you give me a rank decomposition of a function, I can always remove from R and S the common terms, and then I will get another decomposition of the same function, but with R and S, my new R and new S being disjoint. So I will get a minimal rank decomposition. So the question we're going to ask ourselves are first, when are minimal decompositions unique? And second, when do decompositions exist in the first place? Let me start with uniqueness. So here I work in the most general setting. P is a completely arbitrary poset and K is a field. And the theorem says that whenever rank decompositions exist, the minimal rank decomposition, which we know to exist, is unique. And so this follows from the fact that the rank invariant is actually complete in this very general setting for direct sums of segment modules. So it is a known fact that the rank invariant is a complete descriptor for rectangle decomposable modules in the two-parameter setting. Actually, Kim and Momoli proved that it is also, in fact, complete for direct sums of, for interval decomposable modules, and for a large class of interval decomposable modules on certain posets, which are locally finite and so on. But in fact, we generalized this result to prove that the rank invariant is actually complete for segment modules over arbitrary posets. Okay, and from there, it's pretty easy to prove this theorem. It's just a few lines of argument. And now let's go for, so what this means is that basically, whenever you have existence of rank decompositions, well, you have uniqueness of the minimal one. Okay, so you can talk of the minimal rank decomposition whenever it exists. Now let's see when it does exist. So here we need to add a few conditions. We're going to assume that first of all, that the collection of segments over the poset is locally finite. So what does that mean? The collection of segments itself can be seen as a poset when you equip it with the inclusion order. Okay, so we started from poset P. Now we have the collection of segments over P. This is itself a poset. And we're going to assume that it is locally finite, meaning that whenever you have two segments that are included one into the other, there are only finitely many segments in between. This is what it means. And then under this condition, then if you take any arbitrary function that is valued in Z, such that the support is locally finite, then rank decompositions for that function will exist. So what does it mean to have a locally finite support? It means that if you restrict, so the support may be infinite, but if you fix a segment, and then you take the upset of that segment in the collection of segments, then the restriction of the function to that upset is going to be finite. Okay. So in particular, if R has finite support in the first place, it has locally finite support. So this existence theorem follows from another theorem that we proved. It's actually a direct consequence of that other theorem, which I find very interesting. And that says that basically, if you work over the space of z-valued functions on the segments of P with locally finite support, then you have an extended basis for that space. And that extended basis is given by the rank invariance of segment modules. Okay, so the rank invariance of segment modules act as an extended basis for that space. And in particular, if P is finite, or if the collection of segments of P is finite, then the family of rank invariance of segment modules is an actual basis for the space. Okay, so what that means is that every function decomposes uniquely as a z-linear combination of such rank invariants. Okay. All right, so what does it mean for us, for our TDA? Well, we can deduce a number of things. So first of all, in the one parameter setting, we can retrieve known results. We already know that every persistence module admits a barcode. This comes from the structure theorem proved by William Crowley-Bove. So assuming that the module is PFD, but we need to assume it because assuming that the module is pointwise finite dimensional is the same as assuming that its rank invariant is finite. Okay. And so what we know from this theorem is that there is actually at least one rank decomposition of the rank invariant, which is given by the sum of the rank invariants of the segments in the barcode minus 0. And this is the minimal one, and we know it is unique, okay, by what precedes. So basically, in the one parameter setting, there is a unique minimal decomposition, and this is given by the barcode of the usual barcode, I should say, of the module. So this is a sanity check. This is good for us. Now let's move on to the multi-parameter setting. So first of all, the finite case, where your module is indexed over a finite grid. Then the poset is finite, therefore the collection of segments is also finite. So all the conditions on locally finite support and blah, 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 this is all satisfied. These are all satisfied. And if we assume our module to be PFD, then the finiteness of the rank invariant is also satisfied. And so we get as a corollary that every PFD persistence module over that finite grid admits a unique minimal rank decomposition. Okay. So here's an example. Here's an indecomposable module, which comes from embedding an indecomposable of the quiver D4. And here is the corresponding unique minimal rank decomposition, okay, over the segments again. Okay, this is not the unique way to represent this rank invariant as a difference between rank invariants of two interval decomposable modules, but it is the unique way to represent it as a difference of rank invariants of rectangle decomposable modules. This is important. Here's another example, and I like this example because we start from an interval module already, and we see how the interval decomposes through this rank decomposition. So as you can see here, these four blue guys are actually the maximal rectangles included in the interval. And now these red guys are actually their pairwise intersections. And then you have one guy here, which is a triple-wise intersection, threefold intersection, and so on and so forth. And actually, as we will see later, maybe or maybe not, if we can't see it today, you can see it in the paper. Then when you start from an interval module, you see that, in fact, in the rank decomposition, in the minimal rank decomposition, you see the k-fold intersections of maximal rectangles come into the picture. Okay, and there are some cancellations. For instance, in this example, some threefold intersections are the same as the fourfold intersection and so on. Okay, now what can we say in the more general setting? So for instance, if we take P to be Z to the D, then the collection of segments over Z to the D, even though the poset is not finite, this collection is locally finite by our standards. Assuming Fm to be PFD ensures that the rank invariant is also finite. And so we can deduce that if our module has direct summands that have bounded support, then it admits a unique minimal rank decomposition. So why do we need bounded support for the summands? It's because we have this assumption that the rank invariant needs to have locally bounded support. Okay, so this is where this assumption comes from. Okay. And so in particular, if you have summands that are not bounded, you would need unbounded rectangles to represent them, to represent their rank, and unbounded rectangles are not closed rectangles. Okay, they are not defined as the segment joining two elements in the poset. You would have to add some plus infinity to the poset to get this. Okay. So this explains why we need this condition. And now more generally, if we go to the continuous case, for instance, P is equal to Rn, then if we make a more stringent assumption on our module, namely that it has that is finitely presented, then we can deduce that it has a unique minimal rank decomposition. And this one involves right open rectangles. So how can you see that this holds? Just consider that since your module is finitely presented, you can always discretize it over a grid, then apply this result on the grid, and then you can obtain the rank decomposition of P from a can extension of the rank decomposition of the restriction to the grid. And the thing is that can extensions do commute, they commute with rank decompositions. So that's why we get this result as well. Okay. So I can combine this result and the previous one to say that if I have a persistence module over, for instance, z to the d that has, on the one hand, bounded summands, and on the other hand, some unbounded summands, but which are in finite number, then I still get existence and, of course, uniqueness of the minimal rank decomposition for this guy. Okay, so this is nice because we know we have an invariant or a descriptor for our rank invariants, and therefore for their originality modules, which in the form of rank decomposition, so pairs of collections of rectangles. So this is nice. But the thing is that when you start to play out with these guys in practice, it quickly happens that you can't see a thing, basically. So let me show you an example. Here is an interval module. Let me take the minimal rank decomposition of that guy. So the minimal rank decomposition has in its positive part all the maximal rectangles in this guy, and in its negative part all their pairwise intersections. So I could either represent them in a scattered way like this, but then I would have like many pieces to put side by side, and so it would go out quickly of the slide, and they would not be represented in the same frame. And if I want to represent them in the same frame, I get this overlap. It quickly becomes unreadable. And this is still a very simple example, and when you play with slightly more complicated examples, actually, really quickly you can't see a thing. So we were faced with this issue that we had, an invariant that we could not really play with, or that we could not really interpret visually. So the idea we had there was to say, okay, so why not replace each rectangle here by its diagonal with positive slope? So for instance, this maximal rectangle here is replaced by this by its diagonal, which is this blue line. And then this intersection here is replaced by its red diagonal with positive slope. This gives what we call the barcode, the signed barcode of the rank invariant of our module. Okay, so here is the depiction of that signed barcode in this example. So as you can see, you can represent all the rectangles in the same frame, because generically, intersections will be of measure 0. Of course, there are cases where they're not, but generically you can hope that intersections will be of measure 0. Okay, so what is the convention here? So blue, of course, blue bars correspond to blue rectangles, which correspond to positive rectangles in the decomposition. Red bars correspond to red rectangles, so the negative rectangles. And the green dots are the endpoints of the rectangles. Why is it important to represent those? Because sometimes you can have intersections between the bars. That's the big difference with the one parameter case. And of course, you want to distinguish actual endpoints from just intersections. Okay, and so here's another example where we started from an interval module, and where we get another interval module, and where the corresponding signed barcode is this guy. And when you look at the signed barcode, you see the nice symmetry that there is in the rank decomposition, which I was mentioning earlier. So the blue guys here, these four, so this one and this one, this one and this one, give you the correspond to the maximal rectangles. And then the red intervals correspond to their pairwise intersections. And there is this, this middle diagonal, CF, which corresponds to a k-fold intersection for a hierarchy. And here is yet another example, this time on the first example I showed in 2D. And so what we see here is, again, you see the two squares that I was mentioning. And then we see this connection between the two squares. And the whole purpose of this connection is basically to get an extra rank 1 between this index and that index without increasing the rank between this guy and this guy, and the rank between this guy and this guy. So this explains why we have one blue bar and then two red bars to prevent these ranks to be more than 1. And then of course there is an overlap here, so we have to cancel it out. So how do you interpret these barcodes? There are several ways to do it. So first of all, I was mentioning earlier that for one parameter barcodes, you can retrieve the rank invariant visually by just counting the number of bars that connect the downset of S to the upset of T. We have exactly the same thing here. So suppose I want to compute the rank invariant between S and T here. Okay, in this representation of, I took the 3x3 grid, but you have to consider that you're taking a CAN extension over the plane. And so what you would do is that for each term in the decomposition, the rank decomposition, you would have to look where S and T is located with respect to the term. And the only term that gives you a non-zero rank in this case between S and T is this term here. Okay. This you see immediately from the barcode by just taking the lower set of S and the upper set of T, and you just count the number of bars with multiplicities, whether positive or negative, of course, that connect these two these two sets. Okay. Here's another slightly more involved example. So an interval module with S and T in the support. So the rank should be 1. And now if I look at the downside of S and the upset of T, I count the number of bars with multiplicities, with signed multiplicities, and I do get 2 minus 1 equals 1. Okay. So you really get a visual representation of what the rank invariant should be for any pair of indices. I mean, you can infer visually the rank invariant. And so in particular, if you're doing data analysis, you could say, well, if I want to know how many features span, I mean, live on from this index to that index, you can see it from the barcode. Here's another way to interpret the barcodes. If you want to do restrictions to lines. So for instance, if you want to look at the, what is it called? The, if you want to do something a la rivet, basically, you want to compute the barcode, the restrictions of the modules to lines and their corresponding barcodes, you can get that also from the signed barcode. So here's an example, still with an interval module for the purpose of explanation. And so what you would do to get the barcode of the restriction is you would use a property of these signed barcodes, of these rank decompositions, which is to commute with restrictions. And so you basically restrict each term in the decomposition to the line. Each term gives you a certain bar. And then some bars may cancel out. And then you get, by canceling out the bars that should cancel out, you get a minimal decomposition of the restriction. And so that gives you the barcode, as I said, the usual barcode in the one parameter case, as I said earlier. So visually from the signed barcode, you can do the same thing. And basically what you do is for each bar, you project the endpoints of the bar, either vertically or horizontally, depending on whether the endpoint is above or below the diagonal, or whether it's a right or left endpoint. So this is really the same thing as the push operator that we get from the rivet paper. And for each bar, when you project it to the line, you get either an empty set. For instance, for this bar, the left endpoint gets pushed to the right of the right endpoint, so the bar gets canceled. I mean, it goes to 0. And for the other bars, you get an actual interval, but sometimes they do cancel out. Okay. In this example, yes.
Oh, can I pause with a quick question?
Yes, sure.
So does this work if say the poset is Z3 and you're having a 2-dimensional slice? Does it have to be 1-dimensional for things to commute here?
No, we have a more general commutativity result for restrictions and rank decompositions in the paper.
Okay, thank you.
For instance, we're using it for restrictions to grid. When you are in RD and you restrict to a grid, then you can exploit the commutativity of the rank decompositions with restrictions. There are some conditions, though. In particular, you need a lattice structure, or semi-lattice structure. But in some general setting, you do get commutativity. And now the third, maybe the third and more important way to interpret the barcodes is to understand what is the difference between the signal and the noise. Of course, you start from a module and it's rank invariant, and you get this barcode. You want to know what's important in the barcode and what is not. What is really signal and what is noise. What is really persistent and what is maybe just ephemeral. And so the question is, do long bars correspond to signal and short bars to noise, as in the one parameter setting? So I want to acknowledge the contribution of Luis Cocola to this question, because he brought up this question to us. And he also brought up a very nice alternative representation as diagrams. These are not persistence diagrams, but they're very close to it. So the idea is that here we're looking only at the length of bars. So all we care about is not B and D themselves, but it's about their difference. Okay, so whenever you have an interval B and D, you replace it by the difference, the vector, which is the difference D minus B. So compared to the persistence diagram that starting from RD would live in R to the 2D, here we still live in RD, and each bar is replaced by just a single point in RD, which is the difference between its two endpoints. And so what this point represents is how much the interval spans in each possible direction, basically, how far up it goes and how far to the right it goes. And so you can do that for the blue bars, you can do that for the red bars, and for the purpose of clarity, we actually put the red bars in the opposite side of the plane here. So basically here we would take B minus D instead of D minus B, so that we separate the blues and the reds. So here are two barcodes and their corresponding diagrams. We call these diagrams the prominence diagrams because they talk about the prominences of the bars. And so the question can be reformulated as follows. What is the meaning of the proximity of a point in this diagram to what would be the equivalent of the diagonal? So what is the equivalence of the diagonal? It's this cross shape here. It's actually the union of the hyperplanes that are perpendicular to the coordinate axis. So in 2D, it's just the coordinate axis, basically. So this is the equivalent. This guy here plays in black. It plays the equivalent. I mean the analog role to the one diagonal. And so can we say that the point that is close to it is actually noise, whereas the point that is far away from it actually corresponds to signal? And so we dug into this question, and the answer is that well, rank decompositions also commute with smoothings. So the right way to formalize the question is to apply smoothings in the one parameter setting. When you want to discriminate the signal from the noise, you smooth your module, namely you take the image of the module into its shift via the natural morphism between the two. And you look at when, for instance, a particular value of shift, epsilon, you look at which bars disappear and which bars stay. Here we can do the same, and actually we can show that rank decompositions commute with shifts. So here's an example. Again, for the purpose of explanation, I'm taking an interval module, and I'm overlaying its barcode. Now, when I take the epsilon smoothing of that interval module by this epsilon here, what this means is that I shift the interval, and then I take the representation that is indexed over the intersection of the two intervals. Okay. And so here is the corresponding barcode. And there is a nice connection between the original barcode and this barcode of the smoothing, which is given by this result that says that basically each bar here is given by one of the bars over there to which you have applied the smoothing. So what does it mean to apply the smoothing to a bar? Well, you take the corresponding rectangle, you smooth it, namely you intersect it with its shift, and that corresponds to taking the upper right-hand point and basically shifting it by minus epsilon. Okay, so every interval here is obtained from an interval over there by shifting the right-hand point by minus epsilon. Which you can see, for instance, for this guy, it's AD with D shifted by minus epsilon. Okay, and of course, some of the intervals will disappear and others will remain. And the ones that remain will give you the barcode for the epsilon smoothing. And in terms of prominence diagrams, what this means is that you can take the offset of the signed offset of the diagonal by epsilon, which I represented as in light gray here. And basically, the points that end up in the offset disappear from the diagram, and the ones that stay outside become now closer to the offsetted diagonal, and the close and this interval here is the one that you see over there. Okay. So you obtain the prominence diagram of the epsilon smoothing by just inflating the diagonal, as in the one parameter system. Okay. Let me say briefly that this applies to generalized rank invariants as well. So for now, until now, I've been talking only about the usual rank invariant, but so the rank invariant was seen as a function over the segments in my poset, but you can generalize it to become a function over arbitrary intervals in the poset. And so how do you define the rank of a module over an arbitrary interval? So this is a definition given by Kim and Memoli. You simply take the restriction of your module to that interval, And then you take the morphism, the unique morphism, from the limit to the co-limit of that restriction. By connectedness, there is a morphism, and that morphism is unique. And so you can see, so this generalized rank invariant has very nice properties. So it's much harder to compute than the usual one, I must admit, but it has very nice properties. For instance, to be like the usual rank invariant is complete over the collection of segment decomposable modules. The generalized rank invariant is complete over the collection of interval decomposable modules. So what I said at the beginning of the talk was a little bit wrong when I said that the rank invariant was complete over the interval decomposable modules. It's actually the generalized rank invariant that is complete. Okay, so you can do exactly the same thing as we did so far. You can define rank decompositions for these generalized ranks. You can see them when you take a function over the collection of intervals to the integers. You can see a rank decomposition as the difference between the rank invariants of two interval decomposable modules, basically. And it's going to be minimal whenever the two collections of intervals are disjoint. All the arguments that are used in the proof actually don't use the fact that you have segments in the first place. And so they apply verbatim to the case of like more general collections of intervals. So we get the same existence and uniqueness theorems, basically. Okay, so here's an example for the 3x3 grid, where now the collection of intervals is the collection of all intervals of P, and here is the rank decomposition that I get. It is tempting to think that these three rectangles should combine into an L shape like a lower hook, but that is not the case, because if it were the case, then there would be a feature living from here to there. But as you can see, if you go through this map, you do not end up in the image of that map. So such a guy does not exist. So that's why, even if you take all the intervals of P, the generalized rank invariant does not, the decomposition does not aggregate these three guys. And that's an interesting feature because, as we will see later, let me now say just that when you have such a decomposition, you can further decompose it because each term here is an interval module. So you can decompose its rank invariant further over the segments. And so you get a refinement of the decomposition over the intervals as a decomposition over the segments. So you can represent this representation of over the intervals as a barcode, as a signed barcode, which is the one of its refinement. Plus you have decorations on it because you know that you started from here. And so you know that, for instance, these three guys, okay, so let me see who is who. So this vertical guy and this one combine together to become this L shape. And so you can mark it as being like these three combined together. So I marked it as this square. And you can see that these three guys over there, so the two guys and the red guy, do not combine. And that's important. Because if you look at the signed barcode without decorations, you might be tempted to say, oh, I have a feature here. I might have an interval that's an L-shaped, but the thing is that that guy does not exist in the module you're starting from, and this you see from the generalized rank decomposition. Okay. So basically, what generalized ranks provide us with is extra decorations on the signed barcode that help the user get a reliable interpretation. So here are some experimental results, just as a proof of concept. So we started from a point cloud in the plane, as you can see on the left-hand side, and we took a bifiltration, first by radius, so by distance to the point cloud, and second by height, where the plane is oriented. So this is the vertical direction. And we've got three features in one dimension, in degree one, in homology, which are this loop here, this loop, and that loop. Let's call them A, B, and C. And we can see with the naked eye from the bifiltration, because the example is very simple, we can see more or less their lifespan. So the lifespan of A is this full rectangle in blue. The lifespan of B is this L shape or lower hook in brown. And then the lifespan of C is this little rectangle in red. Now, what do we see in the rank decomposition of the rank invariant? We see this. So here we have one bar that corresponds to the rectangle of A. So I have inflated a little bit the rectangle so we can see things. We have one vertical bar here, which is the rectangle of C. And we have these blue and red bars that could combine together to get the lifespan of feature B. Of course, when you use the usual rank invariant, you don't know if they combine or not. You would have to compute the generalized rank over this shape to check whether this object really exists as a feature in the module. But you see, what you can do in practice is you can compute the usual rank invariant, decompose it, get a barcode, and then from the barcode see which bars could combine with which bars, and then check specifically for these combinations if there is a corresponding interval by computing one generalized rank for each combination, which is much better than computing the generalized rank invariant for all possible intervals. Here's another example. So this is still radius in one dimension, and the other dimension is co-density. So density gets, so we filtered the points by co-density. So these are the points with the highest density here. And as you move up, you have points with lower and lower density that appear. You see basically three features in degree 0 this time. So this is clustering. A, B, and C, these are these three blobs. And we see basically, so what is this, by the way? I don't remember what the black squares are. I'll try to figure out what they are later, because this guy should not be here. Give me a second. What is clear here is these three. Oh, I see. No, okay. So this guy is just arbitrary. So we picked this. Okay, so we had picked this particular index to show that there were three features, but then I put the letters over there. Okay. So this is just this particular interval. The index has nothing particular, no particular role to play. But now these three indices are important because these are the indices at which the connected components get connected together. Okay, so here B is connected with C, here A is connected with C, and here A is connected with B. So you see these threefold, these three different connections, and then all three become connected together. So you would imagine that you will have an indecomposable summon in your module. And indeed, here is the signed barcode. So it may look a little bit messy. So let's try to analyze it. So first of all, we have one big bar. Let's look at the bars that start at 0, 0. We have one long bar, which spans the entire bifiltration, and which is actually corresponding to the lifespan of A. So A is this connected component. And then for the other bars that start at 0, 0, we see that there is this nice staircase here. And so we suspect that there is an interval here that corresponds to a single feature, which would be B. And you can double check again with generalized rank that this is indeed a feature and not a spurious thing that appears from the barcode. And then finally, we have, starting at 0, 1, we have bars that combine into these supposed interval, which we can check again by computing generalized ranks. And this would correspond to the lifespan of feature C, which is this guy here. Okay. So that's how you can get information about the formation and the merging of clusters from the barcode. The barcode itself just gives you hints, but then if you compute generalized ranks, you can get confirmation of your interpretation. I don't know if I need to stop now or if I can continue. I still have maybe one more topic that I wanted to look at with some further experiments. But if I'm running out of time, I can stop now.
Maybe to leave time for questions, wrapping up now would be best.
Okay. Okay, good. So, okay. So to wrap up, maybe I should just touch a little bit on this question of stability, because so far we have been defining an invariant or a descriptor and studying its properties. But of course, the question is, how stable is this descriptor? And there is a natural distance to be put, or dissimilarity at least, to be put on these rank decompositions. This is defined as follows. So if you take two rank decompositions RS and R prime S prime, we have the properties that they are rank decompositions of the same rank invariant if and only if R union S prime is actually equal to R prime union S. And so it makes sense when you have two rank decompositions to compare them by comparing basically the interval decomposable module formed with R and S prime on the one hand to the interval decomposable module formed by R prime and S on the other hand. And a natural choice of metric between these segment decomposable modules is the matching distance, because it's naturally tied to the rank invariant. And with this choice of dissimilarity, because this is not a metric for rank decompositions because of the negative signs, you don't have the triangle inequality, but it is still a dissimilarity measure. We have the following stability theorem that says that for any pair of rank decompositions, the matching distance between them, as defined above, is bounded above by the matching distance between the two modules, and therefore by the interleaving distance, and also by the bottleneck distance between the two modules. Of course, if you take two modules M and N, the matching distance that you get between their rank decompositions will depend on the choice of rank decomposition. If you take non-minimal rank decompositions, what can happen compared to minimal ones? In fact, it turns out that the distance is maximized when you take minimal rank decompositions. This makes sense because if you take non-minimal ones, you're allowed to add more stuff, and therefore you can make more complicated matching, so to speak, and between the bars. Okay, and I'll stop here. So the wrap-up will be easy. So this is a new descriptor for the rank invariant. It completely and fully describes the rank invariant, or the generalized rank invariant, if you express it over the collection of all intervals, not just the segments. I haven't shown how to compute it, but we get inclusion-exclusion formulas for computation, which actually are the same as the ones that Kim and Memoli got for what they call the generalized persistence diagrams. And there is, in fact, an interesting connection between the two, which is that whenever the generalized persistence diagrams are defined, that is, whenever you can take Möbius inverses and compute convolutions, these generalized persistence diagrams are give you the exact coefficients in the minimal rank decomposition. Okay, so there is a coincidence between the two, so to speak. And they're stable, of course, as I just said. And finally, something that I didn't have time to talk about, they are also grounded in algebra in the sense that there is no corresponding direct sum decomposition of the module, because we know that this direct sum decomposition, even though they exist, they involve not only rectangle modules, and not even only interval modules, but there are resolutions of the module that correspond to the rank decompositions. Basically, you can show, you can equip the category of persistence modules over a fixed poset with an exact structure, whereby you can find resolutions that are rank exact. So that is such that the rank invariant of the ground module will be expressed as an alternate sum of the rank invariants of the modules in each degree, with a sign given by the degree, basically. And with this, I'll stop here.
Okay, thank you very much. So everybody, please, if you can unmute yourself and applaud the speaker. Okay, so we have now a few minutes for questions. Feel free to, Bei, please ask.
Hi, Steve. So I was curious if there is a geometric interpretation of this process. I think you kind of already hinted on it. You had one of those decomposition where it looked like a Z shape, and you have two small red bars, and you said that the red bars were there to somehow repair, to kind of constrain the rank so that it doesn't go beyond one. So I was wondering if you can say something more general. Is there a very good geometric interpretation of this decomposition? So I think it's a previous picture.
It's hard to answer in full generality. What we know is that for interval modules, there is indeed a clear geometric interpretation in that the one rank decomposition, maybe not minimal, but one rank decomposition is given by taking in degree 0 all the maximal rectangles included in the interval. Then in degree 1, that is with a minus sign, all their pairwise intersections. And then in degree k, that is with sign -1 to the k, their k-fold intersections. This may not be minimal because you can have some k-fold intersections that are the same. So they will cancel out in the end in the minimal decomposition. So there is a clear geometric interpretation. Now, in the more general setting, I am not able to answer the question. I don't know.
Right. So I think the picture is before this.
Yeah, I think it's towards the beginning. I think it's.
Sorry, it's pretty hard to do, but it's one of those Z shape. I guess yeah, right. This picture. It feels that somehow you could start with a blue rank decomposition, and then you notice there's something that needs repair, and then red comes in as part of the repairment. Does this lead to another algorithm? I know you kind of hinted on the algorithm.
Okay. So, okay, now I can answer this new question. Yeah. Yes, so indeed, in fact, initially we had an algorithm, a greedy algorithm that would proceed like this. So first of all, we would look at the support. So we start from an arbitrary rank invariant, even for a module that may be non-thin or non-interval decomposable, okay? So we start from an arbitrary rank invariant, or even an arbitrary function over the set of segments. And now what we look at is the support of that function, and then we take a maximal element in the support. And you can prove that this maximal element has to be in the decomposition. So maximal with respect to inclusion. It has to be in the minimal rank decomposition with a positive sign. Okay. And now what you do is once you have found it, you just subtract its rank invariant from the rank invariant of from your original rank invariant. What you get may no longer be a rank invariant. It's a more general function. And then you proceed like this. You continue. Of course, the maximal element then, the support, the maximal element in the support might actually have a negative rank afterwards. So then that means that the corresponding rectangle will end up in the negative part, and so on. So yes, in this example, it would boil down to, for instance, taking this this rectangle here, which is maximal. So you subtract its rank, and then you take this maximal element, you subtract its rank. And then what remains basically is this rank over there, which is going to be a -1. And so you have to account for that. So now it will be +1, sorry. So then you have to account for no, -1. So you have to add 1 bar connecting the two indices to get 0. But then this creates +1 here and +1 here. So you have to remove these 2 bars. That gives you -1 in the middle. And so you have to add this extra middle thing to get 0. So yes, indeed, there is an algorithm that proceeds like this. So in a previous version of the draft, we were doing this, but then we realized that there was an inclusion-exclusion formula when we realized the connection to generalized persistence diagrams.
Cool, thanks.
We also have a question from Chung.
Oh, hi. So thank you for the thank you for the talk. So I have a question about the generalized ranking environment. So do we know that if we want to compute like this kind of generalized ranking environment, could it be computed in polynomial time, or it could be exponentially many non-negative, like this kind of interval decomposition?
If you work in a fixed dimension, I think this would be polynomial time in the input. But then, of course, if the dimension is considered as part of the input, then it's going to be exponential. You would have something to the dimension that appears.
Oh, okay. So does it mean
because
that
basically what you're going to do is you're going to consider sequences of elements, sequences of chains. You're going to consider a chain, sorry, in your interval, and corresponding sequences of elements, and that map the one onto the other, and there is a polynomial number of those in the size of the input.
So does it mean that if I fix the dimension, so if I fix the number of parameters, so then you can compute a generalized rank environment in polynomial time?
I think so. I'm not completely sure, but I don't think so.
Okay, yeah, thank
The
you.
dimension is considered a constant.
Yeah. Okay. Nope.
Okay, so I think at this point in time, we'll take the rest of the questions will have to be offline. So thank you, Steve, and thank you, everybody, for coming.
Thanks
And I'll
everyone
end the
for
recording.
joining.